Data structure using C++, module 5, session 8. So the last method and last topic of this subject, deleting an element from a binary search tree. So there are three possible conditions which we will discuss, all three possible conditions. Since we are dealing with binary tree, so you can expect a terminal node. Terminal node doesn't have a child. Then you can expect a node with one child, second possible. So this node may have to be deleted. And one more case would be a node which is having two children. We are supposed to delete the node. So these are three possible circumstances for a node. It might have two childs, it might have one child, it may not have a child. So if it's not having a child, then it would be pretty easy to delete a node if it's a terminal node. Okay, for example, let's assume the binary tree addressed as follows. So how the deletion needs to occur. Suppose if I look at this binary search tree, then if I want to delete element 2, it's very easy. Directly you use a pointer, traverse, reach the key element. If the key element reaches your destination, then delete that directly and you don't have to do anything. Whereas if suppose say that 5 has to be deleted, then there is an issue. What you have to do again, you have to create a pointer, make the pointer point here, compare the key value with this element value, and if it matches, then you have to delete this node. So using the pointer itself, we will be deleting, and the child of this has to be connected to the parent of this node. So that has to be done. So you have a program to design for that. And one more scenario would be, suppose assume 30 itself has to be removed. So in that case, you have two options. So if the node which is having two child, if we want to delete that node, then who would take that place? The first case, this place could be occupied by the largest element present in the left subtree. In the left subtree, you can find out that the largest element is 5. This can definitely replace it. Or when you look at this right subtree, the smallest element in the right subtree can also replace. So you have two possibilities. 31 can also replace. So this goes. So we are not concerned about complete binary tree. Here the case is we should ensure that it is a binary search tree. So 31 can sit here, no problem, or even 5 can sit here, no problem. Okay, the structure of the tree would be modified in the same way. And that's which means you have two possible cases. And in this program, we will be using for the replacement of a node which is having two child. Replacement is using the largest element present in the left subtree. That would be the element which gets replaced over here according to the program. Okay, now let's move on to the program. One by one example we'll consider. First scenario, let's assume that the key which you are supposed to remove is 2. And don't get confused. So in the previous insert method, we have taken the node structure as different. That's made that way to make you understand, but literally in the textbook, this way the binary search tree would be given. Okay, so here assume that there is the second element, but we concentrate only on the first element, which is the key value. Fine. Now let's go back to the program. So now the key value is 2, and this is your binary search tree, and that's located here. The key value happens to be there in this binary search tree, and it is a terminal node, and it's easy to remove this. And let's see the program now. So this is your program. The name is erase, and it is going to handle the key. The key will be the argument taken by erase, and this element, if it's present in the binary search tree, that element with a node itself will be deleted off. Delete the pair, whole thing should go, right? So you will be using a pointer, and when you delete a pointer, if you try to make the pointer point to that particular node, and then directly you can use delete function, definitely you will break the link first, and it is going to destroy the complete node. That's what the method which we follow usually for delete method. Now First, you have the condition looking at this scenario. The first case scenario, the key value is equal to 2, right? And we create a pointer first, p, and it will be pointing to the root. Let's say that root element in this binary search tree is 30, and root will point to the first element, root, and say p will also point there. And again, we create one more node as pp. pp stands for parent to p. Parent to p, initially it will be set to null, because literally when p is pointing to root, pp doesn't have a root itself, so that's null. That's not pointing to any node. Later, when you traverse forward, then the pp gets node values. Right now it's null. So first step, we create binary tree node pointer. So what is this binary tree node pointer? This, using this pointers, we can make we can traverse the nodes. It can point to the different nodes, and this node is having element, a pair of elements, which is key as well as the element value associated with the key. And p is pointing to root, and pp is null. Now the first condition, let's try what happens when you execute this piece of code. While p not equal to null and p element dot first not equal to the key. Let's see what the condition is here. So p is not null, that's true, because you have a binary search tree here. It's not null. And the element dot first, element p element dot first. What is p element dot first? P element dot first is this value, which is 30. And that's not equal to the key value, right? It's not equal to the key value. Is it less? We will find. So it's not equal to null, which means we have to traverse. Okay, so inside we will check, we will compare the key value with element dot first value, because we need to figure out whether this is your region of interest or this is the region of interest for the key. Right now the region of interest for the key is this region, so it has to be you need to search on to the left subtree of this. So in the while loop we use that condition. So first what we do is we traverse the p. Now pp gets p, so now pp points where p points. So this is the structure, and we compare p element dot first here, p element dot first, and the key value. Now the key value, is it less than p element dot first? True, because the key value is 2. This is 2, and element dot first value is 30. So definitely the condition is true, which means the region of search is p is equal to p of left child. So p will be pointing to the left child of p. Right now the p is here, its left child is this. So this is where the p should point. So p is pointing here now. This is the structure. Is it okay? Next, again we need to stay back in the while loop. So while loop continues, else statement will not be executed. While continues, again we have p not equal to null. That's true, because right now this is the scenario and p is pointing, it has elements, so it's not null. So in this case what happens, it will again go in and it will check the key value with 5. So now the key value is 2 and it's lower than the p value, right? So first what you have to do, you make sure that pp goes here. Okay, pp goes here. Okay, so that's what is done first initially. So here you are. First pp is made to point where p is pointing. So pp is pointing right now here, pp is pointing here, and when you're executing the next piece of code, it becomes, if the key is less than p element dot first, then p has to be changed to p left child. So what is the p left child? P left child is pointing here. So this is where your p in the next iteration should point, which means this will be the structure, equivalent structure. P is pointing here and its parent is pointing here. Now again while loop gets executed, and in this case p is not equal to null. That's true, that has a value, p is having a value. This is the structure, p is having a value, and p element dot first is exactly equal to key now, right? Which means this while condition will not be executed. So it comes out of the while loop, it breaks this while loop, and what it does is it checks if p is equal to null. P is not equal to null, which means key is there. key is there, the element which you are supposed to destroy is there, right? So what you do is you go to the next piece of code. So remember, this whole set of code right now it's not important, because this will be the scenario when you're having a node which is having two children. Right now the node doesn't have any children, so just you can ignore for the time being what basically is done here. Okay, the next piece of code, even this you can ignore. Till here, this much you have to this is the whole code, that is this two slides, slide number 75 and slide number 76 in this case, both are used for handling when the node is having two children. So right now we will not talk about this. Okay, now the next one, even this one, from this point to this point you do not have to worry. This works when the node contains one child. Right now you don't have a child, so what happens is you just decrement the tree size. Right now directly this instruction will be executed, tree size will be decremented, and you are going to destroy that pointer. Okay, so we were over here, this was this scenario, P was pointing here, destroy this pointer, so this link is broken and this 2 goes. So this is your redesigned binary search tree, wherein the terminal node, which happens to be 2, is deleted off. So that's easy, very simple. So you do not have to worry much about. Now let's take a second example. When you have an element, the key value which you are supposed to delete is fine, and it's available, and right now this key is having one child. Now let's concentrate and understand how this works. Fine. So now this scenario again, here erase function, p is pointing to root and pp is not, that's correct, and p is not equal to null. So what happens, p is not null, that's true, and p element dot first is not equal to the key, that's correct. So here you are, and okay, and what happens now, what you have to do, the element, the key value is 5 and that's lower than 30, so you have to go, p should be travels to p of left child, it has to be done inside the while loop. So you'll be checking that this is your region of interest. So when you're in, pp becomes p, and you check if the key value is lower than p element dot first, and p element dot first value is definitely lower. So the key value, the key value is lower than p element dot first, correct? So you're here, element dot yeah, hold on a second. Yeah, first case pp was here, and p becomes here. Second iteration, p will be pointing here, and when you're entering the while loop now what happens, situation will be in this case p is not equal to null, true, and p element dot first is equal to the key, which means this while statement will not be executing. And here the current scenario is this, right? So p is pointing here and pp is pointing here. Now let's see how this will be deleted. This is your right node which needs to be destroyed. So now first you check p is equal to null. No, that's not null. And next we go here, we check p left child, is it not equal to null? The left child of p, you have 1, that's correct, but when you observe this p right child, that's null, right? So this doesn't have a right child, so it is null, which means this statement is not true. This we will be checking when the node has 2 children. Right now the node is having only 1 children, so this whole piece of code will not be executed. Similarly, this slide will also not be executed, so you do not have to worry about this. But this is only one piece of code which gets executed. Now let's try to concentrate. So what you have to do is observe here. So we have to create a new node in this case. Sorry, this case. So this is your structure now. You create a node and name it as C1. Define a pointer, node pointer, and make it point to the child of this. So how would you get the child of this? P of left child. Make it point to where P of left child points. Then the compare it. So what you have to do is pp of left child. Finally, this one you have to destroy it. So make sure that you connect pp of left child, because pp is known now. pp of left child, you make it connect to c, then you can delete d. So in that case, d can be destroyed. I repeat, what you have to do is you create a node c and make it point to first p of left child. P of left child is pointing here. Make c point there. So when it points, this will be the situation. Then make pp of left child, which is pointing to p now. Instead of making it point to p, make it point to c. Then delete p. So this is how the structure looks. Now let's look at the program. So first we create a pointer c, then we check if p of left child is not equal to null. So in this case scenario, the p of left child is not null. P of left child is not null. Okay, so what you have to do, you have to traverse. So you use this condition, c becomes p of left child. Okay, c becomes, in this case, since it is not null, c becomes the p of left child. So child of p, make it point to c. So only one child, let us say, right? So c points to the child of p. That's correct. Next case, we check this condition. This is false. Then we check if p is equal to root, wrong. Then we check this condition, if p is equal to pp of left child. That's correct. So when you observe this scenario, p is equal to pp of left child, right? So either you can take this figure or you can take this figure. Both case, p is pointing to this node and pp of left child is also pointing to the same node. So p is equal to pp of left child. In that case, make pp of left child point to c. Okay, so that's what is done here. You can see the structure. So if p is equal to pp of left child, then pp of left child, make it point where c points, else other way around. So after this, now your tree structure looks like this. C points here. Okay, and finally this node has to be deleted. So you just delete p, it is going to destroy that node. So, okay, so that's what is done, and ultimately you can just observe, you just use tree size minus minus, then you use delete p. So this way you can delete the program. The last code we will observe the last method, that is to delete using when there are two children. So we will look at it in the next class, because it is huge, you require more time. I'll explain it in the next class. Time being, it's fair enough.